Welcome back. So, we are talking about structural properties, thermodynamic properties, mechanical properties, vibrational properties, which we will spend some time on as we move forward, because some of my research has been in the area of laser Raman spectroscopy and understanding interface phenomena at very atomic level in terms of adhesion of material of different substances. We will come back to that and how we use a combined molecular dynamics simulation and laser Raman spectroscopy techniques to design some of the advanced interfaces. So, with that vibrational understanding, we also look at some of the transport coefficients, and these are the coefficients which essentially are helpful in transporting some of the material or diffusion of the substances, viscous flows, or even thermal conductivity, where you look at the heat transfer. So, we look at the transport of material, which is fluid mechanics, fluid transfer. We look at the diffusion of different kinds of dye within the liquid systems and how they diffuse through it, or even carbon monoxide and carbon dioxide in atmosphere. You want to look at the diffusion of those, as well as the viscous phenomena, where you are looking at the viscous material and how does that move using some of the Navier-Stokes equation, where you have understanding of the fluid flow where the fluid systems are viscous. So, with that understanding, first we start with some of the properties that we calculated as given here. Look at the total energy, temperature, pressure, specific heat, radial distribution function, diffusion constant, and velocity autocorrelation function. So, these are the properties we will focus on. So, first order business here is how do we calculate these properties? We are doing time average. So, if you look at any property that we are calculating, first we are going to calculate instantaneously, then we will create time average over number of time steps. So, that gives us good idea about the trajectory of n number of such atoms, and once we integrate over n number of such atoms as given on your slide here. So, we are looking at the average over time, so 1 over t, and then we are looking at the fluctuation of any property A with respect to time. But now, because we have n such time steps, so instead of doing integration sign, we do summation sign, and the summation sign is for all particles from 1 to n, and we are looking at time average at t k, and that is where we create the time average. So, if there are two different properties that we are looking at, then we can also create property in terms of cross correlations. That is general framework. Then we get into the temperature. As you know, temperature is easy to formulate because we know the velocities, and these velocities are connected with the equipartition theorem, and that gives us kinetic energy, which is half mv square. But now, it is calculated over the time trajectory. So, you will look at if you look at the pair potential, you are able to look at I j. In this case, we are only looking at the particles j over n number of such particles, and we are looking at kinetic energy on each particular particle. Then, when you go to equipartition theorem, then you say temperature is equal to 2 over 3 k, which is Boltzmann constant, and multiplied by nkb, which is the Boltzmann constant, and k is the kinetic energy, which is essentially given by half mv square. So, if you know the velocity, you can plug k, which is the kinetic energy term, into t. So, you have kinetic energy, divide that by 2/3 of number of particles and Boltzmann constant kb, you get a thermodynamic temperature there. Now, if you look at the potential energy, that is only a function of space. We are looking at how the position vector is changing. Based on that, the potential energy can be calculated, and you can calculate it at every 10 time step and then do the time average. Pressure is bit difficult quantity, but we use equation of state and come up with the virial coefficient, the first virial, in order to calculate pressure. So, in this case, pressure has one term which is coming as from the equation of state, the simpler model, which is gas constant P v is equal to mRT. But now, in this case, we are looking at the virial expansion of the equation of state, which is not simply P v is equal to mRT, but and it also has virial coefficient of that. So, in this case it relates with the volume. So, the pressure is over n kBT, which is the kinetic contribution to the pressure, almost like atoms hitting the wall and creating pressure there. And then you go into the volume part of it, because this pressure is related with the volume. And then we are looking at the force vector multiplied by distance vector on the time average. So, now we are looking at the changes in the potential energy function, where with respect to the time, and that is providing us configurational energy, which is contributing to the pressure. So, if you look at other measures, then we can look at other physical properties to create other thermodynamic quantities. So, if you look at the total energy physical property, which is just the summation, again we are look at the two summation between pair potential. So, this is for good for the pair potential, like what we looked at the Lennard-Jonesian system. So, in this case the total energy E is equal to nothing but 612 potential. So, we are looking at 4. Now, starting with the first summation or the first loop, which is starting from I is equal to 1 to n minus 1, and then you are going to j greater than I to the n. So, now this is the pair I j, and so we start with 1 and go through all other j atoms, and that is how we create the pair potentials. And for this R I j, we can calculate this part is the potential energy part, and this part is the kinetic energy half m v square in the reduced unit. So, now you have the total energy part. Now, if you look at the temperature, as we saw earlier, T becomes 1 over 3 n minus 3. These are the degrees of freedom, then half m v square, and then we also have the term coming out of Boltzmann constant that we looked at earlier. T becomes 2/3 of potential energy function multiplied by n k b, which is the Boltzmann constant. Now, as we said in the pressure term, we are now looking at the calculation in the pair potential term. So, if you look at earlier the temperature for the pair potential, where it is V I j, if you know the velocities of individual particles, then we have very simple formulation here for calculating temperature. Now, if you look at the pressure for the for pair potential, then also there is some simplification. Omega is the volume, n kBT essentially provides you the baseline energy of the system. And so, if you look at P omega n kBT, you can see the pressure related with the equation of state, plus 1 plus 8 over n T, which is the temperature. And you are looking now again average, time average, represented by these two brackets inside the two summation, again from I 1 to n minus 1, j greater than I to the n. Now, you are looking at the 2 R I j minus 12 minus R I j minus 6. So, now you are looking at this is the potential contribution, configurational contribution to the pressure, and there is a contribution which is coming out of the kinetic energy. Now, we come up with the specific heats, which is an important to find specific heats in solid, liquid and gaseous phase, as we discussed earlier. So, in that case we are essentially calculating the K, which is connected with the specific heat in terms of 2 over 3 n 1 minus 3 n over 2 C V, which is where we are connecting it with the specific heat, and that is connected with the essentially a if you look at the standard deviation in terms of the central value of the kinetic energy. So, you look at the kinetic energy average, kinetic energy instantaneous, and if you average over the entire kinetic energy of the particle, now you can relate that with the degrees of freedom. And as you saw earlier in our thermodynamic situation, that each degree of freedom contributes 1 over 2 kBT, which is essentially the Boltzmann constant. So, we know that each degree of freedom will contribute to a specific heat, and we can then calculate based on the kinetic energy, we can and the degrees of freedom, we can calculate that. So, I think at this point let me stop here and give you some example from VMDL that we have been using. So, we are going to look at pressure calculation using VMDL, and in this case we understand the pressure as a quantity of a pure substance and see how we can calculate that. Thank you.